what this sine and cosine looks like and why it looks. I think I talked a little bit about it last time, but I probably wasn't terribly successful with it. Okay, go across. Now the first thing I'm going to do is I'm going to try to draw a circle here. And I'm going to use 1 unit to make sure that okay, I think if I do it that way. What I'm going to do is I'm going to use 2 blocks or 1 unit. So I'm going to draw this half a circle here. Okay. So the center of the circle is going to be there. So this is the center, and then it's 1 unit high. And what I'm going to do is I'm going to go over here and I'm going to draw an XY coordinate. I'm going to call this 1 unit, positive 1, and a negative 1. So this is essentially the unit circle. Okay. And then the points on the unit circle, this point right here is going to be x is 1 and y is 0. And what I'm doing is I'm kind of breaking this into two different coordinate systems. And I'm going to graph this circle where it has a 0, 0 here, and then I'm going to roll it out on the line so that this arc starts right here and rolls out this way. And this is what we're going to do to try to illustrate what is happening. Now here, the x value is 0, the y value is 1. And back here, the x value is a -1, the y value is 0. And here it's the x value is 0 and the y value is -1. Now, I'm gonna be talking about the sine curve. So I'm gonna go y equals sine x, where x is going to be where I'm at on this arc, and y is going to be the sine of that. And remember, the sine is what? It's the vertical, right? It's the y component, but, right? So the x is going to be the arc length, which is equal to the central angle in radians on a unit circle. And what I'm going to do is I'm going to start this arc and have this point be the arc at 0. And then what I'm going to do is I'm going to make this be a completely rolled out arc. It's not going to be quite perspective, but the fully rolled out arc is going to be 2 pi, right? To make one time around. All right. And then if I go halfway, I think I went 10. So 1, 2, 3, 4, 5. So this is rolled out halfway, right, over to here. And then if I go half of that, this is rolled out to pi over 2. This is rolled out to pi over 2. So here is 0. That's this point right here. This is pi over 2. And this is that arc rolled right out to here, right? That arc of just unrolling it. Do you understand, Lucas? Jensen?
Rolled out like a cable.
Yeah.
Pi over 2 on the circle and pi over 2 on the line.
Yeah. Yeah. If this were the front wheel of a bicycle, and this was the line that it, well, you know, like a chalk line on a football field, right? You have the thing like that. Well, it isn't a wheel, but it's like a measuring wheel that you measure, and the distance around it is 2 pi on the circumference, and I'm just laying it out. Okay. Then what it is the height, this height is going to be y, the y value, y coordinate on this going around, right? So wherever the y value is, that's where it's going to be. Well, then what I can do, if I call this, if I call this pi over 6, and I call this pi over 4, and I call this pi over 3, so then if you see pi over 2, if I go halfway, wherever that is, about right here, that's pi over 4, right? And if I divide this into thirds, this is pi over 6, this is pi over 3. Now what's going to happen is, when I'm out here at pi over 6, I'm going to be right here at that point, right? Because it's this height is going to come right out here. Correct? And then when I'm at pi over 4, when I'm at this point, it's going to be this height. See what I'm doing?
Straight across.
I'm just going straight out from here. Straight out from here. And then at this pi over 3, I'm going to go straight out from here, and then I'm coming up. So when I'm at this distance here, I'm at this height. And then once I get out to pi over 2, I'm right up here. Now, it should be nice even curve like that. And then see what happens when I come around here. When I go 2 pi over 3, 2 pi over 3, I'm at this same height, right? Right here. 2 pi over 3. And then when I'm at 3 pi over 4, I'm at this height. And when I'm at 5 pi over 6, I'm at that height. And then when I'm at pi, I'm down there. So then what you do is you just bring those things across. So, and then I have to divide this line up. Halfway is pi over 4. And then I go there and there. So this is 2 pi over 3. And then 5 pi over 6. then I bring these across. So at here, I'm going to be up there, and I'm going to be down here. I should change my color to red. And I'm going to be down here, then I'm going to be here. So that's laying the arc out and then graphing the sine, the y as the sine of that. Now, you can do the same thing that when I go down here, right? Do you see what, in that 3 pi over 2, which this is 3 pi over 2 down here, I'm going to be down here at -1, right? And then at 2 pi, I'm going to be right here. So what it's going to do is it's going to go down. And I've rolled around once. I've rolled one round of my unit circle out once. And then what's it going to do after that? It's just going to start over again, right? That's the period. Of y equals sine x. Now, notice what this, when you're talking about graphing it, at the beginning of the period, 1/4 of the way into the period, 1/2 of the way into the period, 3/4 of the way into the period, end of period. And if I use those words, beginning of the period, I'm at 0. 1/4 of the way in, I'm at its maximum. 1/2 of the way, I'm at 0. 3/4, I'm at its minimum. End of the period, I'm at 0. Now, rather than saying 1 and -1, it's better to say max and min. The 0 is, we're gonna have to rephrase the idea of 0, because if this curve is moved up, vertical transformation of the problem, then it won't be at 0, it'll be at its axis symmetry. Because this what we're going to do is we're going to take this particular red line and we're going to move it up and down. We're going to make it taller and shorter, and we're going to stretch it out and bring it in. The period is this way. The amplitude makes it taller and smaller, and a phase shift up or down is going to be this way, and we're going to talk about it in all those ways. That's why this is the way you should always think of the sine curve. Beginning, you should always know what the period is you're talking about. The period should be when it makes one normal cycle. And at the beginning of the period, it's 0. 1/4 of the way in, it's always going to be maximum. Halfway, it's back at its 0. 3/4 of the way, it's at its minimum. And at the end, it's at its 0. That's the way it's always going to do it. Now, we can actually take that red line and we'll flip it over. And then that'll be done. All it'll take is just a minus sign right up front here. It'll flip it over. Then you have to realize that you're going the other way, right? Beginning and end. You go beginning, 0, 1/4 the way in, minimum, halfway 0, 3/4 maximum, and at the end 0. If you wrote, right, you can visualize that. Rotate the red line around the x-axis. What? Negative sign right in front of here will do it. That'll rotate it. No. I'll show you cosecant. Now, I just look at the explanation on 145 of that sine function. Now notice they have two periods of that sine function graph on 145. They have the one back on this side, right, to the left. You see that? And they have this one that I've graphed, which is to the right. You see that? Okay, so there's two periods. But from here to here is a period. And it's, in this particular case, it's 2 pi long. Now, it doesn't necessarily have to be 2 pi long because you can change the period. Now notice the explanation down there below the billets in that box. It says the graph is continuous over its entire domain from minus infinity to plus infinity. This thing just goes on and on, right? Its x-intercepts are of the form n pi, where n is an integer. So notice that integer 0, 0 times pi, you're at 0. At 1 times pi, you're here. At 2 times pi, you're at here. At 3 times pi, right? If you go back this way, you'll be at a negative pi, negative 2 pi, negative 3 pi, and so on. That's where you're going to cross here. And it says its period is 2 pi long. That's how long it takes to make one complete cycle. And it says the graph is symmetric with respect to the origin. And the reason they're saying that is that respect to the origin, symmetry, if you were to graph this, you see if I went from here, let's see, this is 1, 2, this would be where it would get its minimum. So, symmetry to the origin says that this point right here, let's do the one, is x is pi over 4, and y is the square root of 2 over 2. Now back here, at x is negative pi over 4, this point right here is going to be a negative pi over 4, a negative square root of 2 over 2. If you, every point on this side that's on the graph, if you simply change the signs, that point will lay on the graph back here. And it's symmetric to this origin point. And it don't make any difference where you go, any place out here. If you just reverse, if you just change pluses to minuses or minuses to pluses for every one of those values. And that's called symmetry to the origin. Now here's another way of looking at that. You can visualize that. And you can have to look at the book to probably get a better idea, but you realize it goes down here, comes back up. You see, if I take that red graph, and if I rotate that red graph on the x-axis, and then rotate it around the y-axis, where does it fall? Visualize it. Take the red graph, rotate it on the x, then rotate that onto the y. Where am I at? Do I fall right back on the graph itself? Well, that's, but I think that necessarily doesn't indicate that it's symmetric to the origin, what you're talking about. But if I can take the graph and double rotate it, and it don't make any difference. I could rotate it around the y first, and then rotate it around the x, and where's it going to be? Right back on itself. The double rotation works. Now we're going to find that the cosine function doesn't have that symmetry to the origin property, but it has symmetry. But any questions? And the idea of the length of the period and what happens, those words that I said, you take the period, you figure out what period you're dealing with, and you divide it into 4 equal parts. Start at the beginning, and it's going to be 0. Fourth away, it's max. Halfway, it's 0. 3/4, it's at minimum. And at the end, it's at 0 again. Now, I want to want to point out something, right? The amplitude of this 1 unit circle sine function has an amplitude of 1. Means it goes up from its horizontal axis 1 unit and down 1. It's amplitude. On 147, at the bottom of the page, it's telling you that if you put some number out in front of here, if I wanted to change this amplitude from 1 to 2, I would simply put a 2 out in front here. Now, then I could say, I could still graph this thing, because I would say its period is from 0 to 2 pi. I divide that period into 4 equal parts. Then I would say at the beginning, when the number 2, I'm talking about this, 2 sine x. Now if I was going to graph that one, the period's still going to be 0 to 2 pi, and it's still going to be beginning, 1/4, 1/2, 3/4, end. But at the beginning it'll be 0. This one, 1/4 of the way through, which is right here, it'll be at 2, its max. This one's max amplitude will be 2. It'll be back at 0/2. At 3/4, it's going to be at its minimum, but the one that has 2 in front of it is going to be a -2. See, this is -2, and then that's +2. Oh.
Sorry, can you say that one more time? Because y equals 2 sin x.
2 times sine of x.
Okay. So I mean its max will be 2 and its minimum
This will tell you what its amplitude is.
it'll tell you the amplitude. Okay.
And if that were 1.5, or if that was 1/2, that's the amplitude would be that.
Okay.
And so what you would do is 1/4 of the way in, you would have it be whatever this number is.
You can tell.
Okay. So this one, I would graph this one, if you grant me a little bit of slack here. Roughly look, it should be this one just expanded. Okay. Now, what that is that's amplitude modulation. AM radios, right? What do AM radios frequency look like? They'll be a little small, and then they'll jump up. The period will stay the same, but it'll just get higher or lower. AM, amplitude modulation. And that's what happens. This thing will go to 2, and it'll go to 1/2, 1/4, 3, down, 8, down, depending on the voice or whatever it's transmitting. That's an AM modulated radio. Now, what do you think FM modulation is? It's taking that red part, squeezing it together and stretching it out. Same height, but it just goes back and forth like an accordion. And that's what you can think of. It's just an accordion that the height stays the same and it just goes back and forth like that. That's an FM radio frequency. That makes sense? We're going to see how to modulate it that way. But notice that they're saying that whatever number is out here, that's going to modulate it up and down. Amplitude. And the amplitude is going to be the absolute value of this. They're going to talk about the period, and notice that they're talking about the period. This is amplitude change. Now, if you want to go period change, that is how long this is, that would be something that would be like this. I can use the same number 2, but I would put it right in there. and that's going to be period modulation. And what that'll do is that this actually makes this go, stretches it out, because it'll make this be 4 pi. That thing will happen over 4 pi rather than 2 pi. I think. I got to think about that. No, it'll be pi. It'll do it from 0 to pi. It'll shorten it up. Yeah. I'll show you how to figure it. But the point is that this numerical coefficient of that variable will modify the period. When it's out in front, it modifies the amplitude. Same basic shape. It's just has, you know, different at its quarter points. It's going to have different values. And you can see that if we're talking about frequency modulation, shortening the frequency up and lengthening the frequency, then our amplitude will either be longer, our frequency, our period will either be longer or shorter. We will still, if it's longer, we'll still divide it into 4 equal parts, but each part will be longer, right? And at 1/4 it'll be max, half it'll be 0, and 3/4 will be min. But it'll be over a longer or shorter. So the idea of learning the words is really important. All right. Any question on sine? I might have time to do cosine. Now cosine, let's see, what did I did 4. We're going to have the same unit circle, and I'm going to do the same thing with this. I'll call this 2 pi, which is running that circle 1 time around, and then I'll divide it in half, right? So I'm going to make 4 equal parts. I think it's here. Is that half? So this is pi, right? Because this unit circle is going to have 2 pi length for the period. And I'm going to go half the way here. This is pi over 4. And then this is 3 pi over 4. Now, this is 0. That's going to correspond to this point right here. This is pi over 2. This is pi, 3 pi over 2. And so that'll correspond to those. This, I got pi over 4. Why did I do that? Pi over 2, 3 pi over 2. Because this one corresponds to that. That corresponds to that one. Okay. Now, the difference here is that we're going to do the equation y equals cosine x Now, at this point, at the beginning, our ordered pair is 1, 0. So that means what? That means at the beginning here, I'm going to be this value, 1, right? I'm going to start right there, right? Because so I'm going to have this distance is going to be measured here, correct? Because it's always, the x value is the cosine. And then if I do the pi over 6, the pi over 4, and the pi over 3, lay this thing out the same way, this is going to be halfway is pi over 4, someplace right in here. Did I measure that off right? Pi over 4. Here's pi over 6. And pi over 3. Now notice that at pi over 4, which is this middle one, it's going to be this one right here, correct? At pi over, I'm doing this wrong. At pi over 6, it's this length right here. At pi over 4, it's this length right here, which is the same as the height. Square root of 2 over 2, both of them are the same, right? So it's there. But at this pi over 6, it's this length, which is this height. And then at pi over 3, it's 1/2, right? So it's here. And then it goes down. So it goes this way. And then here it reaches its minimum, which is that length right there coming down here. That's a cosine curve. Its period is 0 to 2 pi. It has 2 pi period. And notice what's going to happen to it? You'll put them end to end like that. But now then, at the beginning, what are you at? The max. 1/4, you're at 0. Half, you're at minimum. 3/4, you're at 0. And the end, you're at max. Okay? Sine is beginning is 0. 1/4 is max. Half is 0. 3/4 is minimum. End is 0. Cosine, beginning max. 1/4 0. Half minimum. 3/4 0. End max. Are you good with it, Lucas? Okay. Now look at this one. When it goes back here, back at 2 pi. And it goes down like this. Now, this one is not symmetric to the origin. You see this? But do you see what happens if you rotate it around the y-axis? What does it do? Falls on itself, don't it? A rotating this on the y-axis falls on itself. Right? Falls right back on itself. Take on the y-axis this way. Take the board and just hinge it right around. Do you see that, Lucas? Now that is an even function. It's symmetric to the y-axis. Because if you rotate it around the y and rotate it around the x, at the beginning it would be at its minimum. It's not symmetric to the origin. It's not the double rotation thing. It's just a single rotation. And it's symmetric around the y. Still has an amplitude of a period of 2 pi, the normal y equals cosine function. You can change the amplitude by doing this number out in front here. You could change the period by doing a number in here, just like this. And the statement for the cosine function is on 148. All right, I'll let you go.